Alrighty, so everyone is still coming, and I'll do a quick announcements and then introduce our speaker for this evening. So this session is being recorded. You'll be able to access it in 24 hours, and by the end of this week, we'll have it up for about 30 days. We'll have time for questions and answers about the 15-minute mark. So 2:45, we'll end the presentation and be able to ask questions in the chat box, Slack, or you can unmute yourself and ask your questions that way. And this webinar is going to end at roughly 3 o'clock because we do have another webinar right after. And with that, I'll introduce our speaker for this evening, Joe Mazzarella,
yes,
from Caltech.
Can you all hear me okay?
Yeah, I can hear you.
Okay. Shall I share screen now?
Yes, sir. Let's see if it works for you.
Okay. Can you see that all right?
Yes.
Okay, great. Well, so welcome everyone. Thank you for taking the time to attend this webinar. I'm Joe Mazzarella, the science lead of the NASA IPAC Extragalactic Database. On behalf of the NED team, I'm going to highlight recent updates that have grown the systematically merged data and derived quantities to over 1 billion objects. I'll also review new and improved capabilities of the user interface, and I'll close with a brief overview of work in progress and plan to facilitate research in powerful new ways using joint multi-wavelength data. So for those of you who may not be familiar with NED yet, new to the field and so on, this is a very brief overview. NED's a service that accelerates and simplifies research for scientists, educators, and students around the world by distilling and synthesizing data across the electromagnetic spectrum from space missions, ground-based sky surveys, and the peer-reviewed literature in order to provide a comprehensive panchromatic census of objects beyond the Milky Way. NED currently contains about 14 billion photometric data points, 1.5 billion multi-wavelength cross IDs, over 1 billion distinct objects, 52 million object links to references, 8 million redshifts, 2.5 million images, and much more. On the right here is a summary of the kind of types of information that we have in the database. Published information includes object names, coordinates, redshifts, distances, fluxes, sizes, various galaxy attributes, classifications, references, and notes. There's also an archive of contributed images and spectra. And we also derive quantities, distances, metric sizes, spectral energy distributions, luminosities, velocity corrections, cosmological corrections, and so on. So all of these data are joined and related in a way that enables powerful science queries. For example, what is the spectral energy distribution spanning gamma rays through radio for the quasar 3C279? What gravitational lenses are known surrounding Abell 68? What objects have published redshifts greater than 7, say? What is the most precise redshift independent distance measurement to M82? What spiral galaxies contain type 1 AGNs? And more recently, with the gravitational wave service, what's the best candidate galaxies for hosting the latest gravitational wave event from LIGO Virgo? So NED is all about fusing sky survey data with data in the literature to simplify research. Joining data from very large and uniform sky surveys is essential for studies of galaxy evolution, dark matter, and the cosmic web. We use a probabilistic cross-matching process after finding candidate galaxies within a reasonable search radius. The local object density is used to estimate the contamination rate, and Poisson statistics are used to balance the match completeness versus reliability. The past few years, we've used this process to fold in data from 3 major NASA missions, 42 million ultraviolet sources from the Galaxy Evolution Explorer, GALEX survey, 141 million sources from the 2-micron all-sky survey, 2MASS, and most recently, in the fall of 2019, we released the results of folding in data from the largest catalog integrated into NED so far, 747 million sources from the Wide Field Infrared Survey Explorer, all-wise source catalog. So this was enabled by almost a 10 times increase in the data ingest rate. About 207 million sources, or 41%, were matched with prior objects, and the rest are new to NED. This is the outcome of the cross-matching process. The 4 bands of mid-infrared photometry have been merged into spectral energy distributions, SEDs. And with this accomplishment, NED surpassed 1 billion distinct objects with cross-IDs, and it's grown to contain over 14 billion photometric measurements. This chart on the left shows cross-IDs established by NED, resulting in the attachment of about 4.2 million of attachment of redshifts, for example, from the Sloan Digital Sky Survey and other surveys to these all-wise objects, which enables derivation of their physical properties, such as, for example, stellar mass. So moving onward now. So completing the large survey catalogs, complementing these large survey catalogs, the team is continuously integrating data from diverse origins in the peer-reviewed literature. These are some highlights of recent NED content updates that have featured data in the literature. In February 2020, so basically these are highlights since last WS meeting. In February 2020, we released results from one of the legacies of the Arecibo Observatory that, unfortunately, as many of you know, recently suffered crippling damage. This was the Alfalfa Extragalactic H1 survey led by Martha Haynes. All of these sources are represented in NED. We're also pleased to report that the 31,000 spectra from this unique survey have been integrated into NED. However, with that comes some bad news. Due to budget constraints and the need to focus our resources on keeping up with the basic fundamental measurements of galaxies, unfortunately, we're no longer able to fold images and spectra into NED going forward unless the funding situation changes. So this is indeed one of our a really great data set to have gotten in there before that unfortunately has to close. In the June release, this is the result of processing 665,000 sources from over 1,700 journal articles. Some of the highlights are here. The cross-matching results led to 232,000 sources cross-ID'd with prior NED objects and 22,000 brand new objects to NED. All of these sources are linked to the references, again, over 17,000. So just a couple of highlights from that. New data from the Cosmos field for 82,000 objects, 823 Fermi gamma ray sources from the Fermi all-sky variability analysis, 450,000 new photometric data points integrated into SEDs, and almost 150,000 new redshifts, 3,000 new supernovae published through December 2019. Some of the main sources for this is the All-Sky Automated Survey for Supernovae, Transient Name Server, and the Sloan Supernova Survey. And also gamma ray bursts information about them is folded in on a regular basis, along with new articles into the level 5 knowledge base. Excuse me, just one moment. Okay. All right, so these are highlights of a more recent release in December of last year. This is the result of processing over 2 million sources from new articles. So the cross-matching results resulted in 387,000 sources matched with prior NED objects and 92,000 new ones. Some examples of these fantastic data sets: 22,000 galaxies and redshifts from the Lemos Spectroscopic Redshift Catalog, and also from the Lemos Quasar Survey. An example of some graphics from that is shown on the right. ICRF positions from structure effects for 3,417 celestial reference frame radio sources, an article from Zuidal. Again, more supernovae and additional redshifts, 320,000, 3 million new photometric measurements. So you get the idea. This is the kind of extensive data that NED releases periodically. So with all this work, this is a interesting overview of all the photometry that's currently fused into NED. We're zooming out here into a global view of all this photometry. So accounting for the multiple spectral bands and measurement methods, NED currently has about 14 billion measurements, as I mentioned before, and these are combined across the spectrum on an object by object basis into SEDs. This extensive synthesis really provides a unique resource for a variety of scientific purposes. For example, planning future observations, filling in gaps in data, resolution, sensitivity, performing object type classifications, whether that be galaxy, AGN, star discrimination, modeling the physical mechanisms responsible for the radiation, and of course the opportunity to make discoveries directly from the database. On the right here is a histogram of the number of photometric data points in NED across the spectrum. So this spans 22 orders of magnitude in energy from radio to gamma rays, as you can see. These data come from basically almost every ground-based and space-based professional telescope as far as data published in literature and in catalogs. This includes 26 NASA missions. And the largest contributors in each of these spectral bands is shown. I won't read through them all, but you can get a flavor for that. If you have any questions about that, you can ask me later. Again, the big takeaway is the extent of these data and that they're matched across the spectrum for objects. Now we're going to have a deeper look into that. So this is a look into how these photometric measurements are joined across the spectrum for the distinct objects in multiple spectral regions. The plot in the upper right here is similar to the previous histogram, but this time the counts are binned into 10 major spectral regions. And again, this is logarithmic, of course, so very, very large numbers here. In this lower plot, we're asking the question, how many of these objects have photometry joined across 2 or more of these 10 spectral regions? So the number of spectral regions covered is on the x-axis, log of the number of objects on the y-axis. So some of the key points in green, the green points show that in 2015, most of the 250 million objects at the time had photometry available only in one band. You can see this here in the first point. And this is mostly visual data from the Sloan Digital Sky Survey. These blue points show the growth of the data over the past few years. This arrow points out that the number of objects with photometry joined across 4 spectral bands has increased by a factor of 1,000 to about 70 million objects. Likewise, the number of objects joined in 6 to 10 spectral regions has increased by about a factor of 10 or more. And on the far right, we can see that there are a few thousand objects, mostly AGN, that have at least one photometric in each of 9 spectral regions. And by sliding, what this line shows, what this is meant to show is by sliding this horizontal line up and down, we can infer what the corresponding spectral regions are. For example, for these objects spanning 4 regions, you can see the data come from the mid-infrared, all wise mostly, near-infrared, 2-mass, visual surveys, many of those in NED, and the ultraviolet dominated by Galax. So again, quite a tremendous set of data for doing science with spectral energy distributions and so on. So of course, SEDs are very important for understanding the energy sources in galaxies, luminous infrared galaxies, AGN, objects of all sorts. These are 2 examples with very wide spectral coverage. The blue points is a radio loud AGN 3C279. And the red points are data from the ultraluminous infrared galaxy NGC 6240, which contains dual active nuclei. I wanted to point out too that again, these are data from more than 20 telescopes and dozens of journal articles, and these 2 plots were generated right out of the NED interface, out of the new interface, and overlaid, and then the annotations were added in PowerPoint. But other than that, this highlights information right out of the NED interface. So also released earlier this year, there's a new sky survey. Oh, sorry, did I miss? Yes, I'm sorry. We're moving on now to review what's new in the user interface. So the January 2020 release highlighted a really great achievement. NED's always connected users from data points in the database to the originating article, but that's been one at a time. Early last year, we released an extension of this capability by clicking on the button that you see in the upper left, usually in the NED output tables, view references in ADS. This ships up a list of up to 50 selected ref codes right into the into the ADS interface for further analysis. And also while we're here, as a reminder, there's strong connectivity between ADS and NED in the other direction as well. This red box highlights the link. Many of you have probably noticed in ADS, when an article has information about objects that are in NED, this uses metadata that we provide for the ADS. You can click there and it runs a query back on NED. So we are highly connected. Also released last year, a new sky survey coverage tab is available in the reports for single object queries. This has a 2-mass sky survey image in the background with the selected object in the center. And then overlaid on this is a map showing the coverage of the Sloan Digital Sky Survey in orange, and a map for the GALAX survey coverage in green. The technology used under this includes hierarchical progressive survey images, HIPS, and multi-order coverage maps, mock maps, and this is enabled by the IPAC Firefly package, providing connectivity to data sets at URSA, CDS, and elsewhere. With this feature now, NED users can determine whether a source is missing data in a specific band because it was not detected or because it is outside the survey footprint. As you can see, there are gaps in a lot of these surveys. Okay, onward now to, as some of you know, in 2019, in time for the 3rd observing run of the LIGO Virgo gravitational wave detectors, NED released a gravitational wave follow-up service. It's designed to leverage data in NED to facilitate the rapid identification of electromagnetic counterpart. Basically this service was released, and this involves doing a 3D volumetric search on the air volume provided by LIGO. In January 2000, the service was extended to include galaxies out to a gigaparsec. We also released a video tutorial in February and documentation of the API. And just briefly, brief reminder, sorry about that. LIGO Virgo is being upgraded now. The next run will commence in 2020. Onward now to the August 20 release of NED. NED's custom legacy author search was replaced recently with another leap in interoperability with the ADS. There's a new form, references by author name form under the literature on the top menu bar, as you can see here. And what this does is it implements an author name search in ADS constrained to articles with objects in NED, which is precisely what we were doing in the old service. But this time we're actually using ADS to do that search. It uses the interoperability of the ref codes, the bib codes, information about what objects are in the articles, and of course the excellent API provided by ADS. You can also input filters such as the caret in front to constrain to first authored papers, if you like. In August, we also released a link to the URSA Finder Chart service, which is very handy. This appears in the overview of the single object query reports. By clicking here, you can get a nice summary of all kinds of other additional data that are not directly in NED. These are in URSA. And the SED plots also now have upward pointing error bars. Another feature released in our most recent release here in January, just last week. Searches for objects in a ref code respond much faster now than before, with up to 1,000 records are displayed with the link to download the full results. This paves the way also for soon updating the links from ADS to point to the new interface rather than the old one. Also in this release last week, another big improvement is long entries in the notes and references tabs of object search results can now be accessed in their entirety. You can click on the little ellipse that occurs at the end of the row, and a little menu pops up, and you can display the full content. We've also changed the default size of the output records so to minimize paging, and a number of other user experience improvements. Okay, on now to a real brief overview. Along with all this work with the data and the interactive human UI, NED also provides application program interfaces with VO standards. We have a table access protocol service, a simple image access service, a simple spectral access service for the SEDs. This year, we plan to update that, following more closely to the VO spectrum data model, and this will simplify unit changes and other capabilities in the interactive Firefly-based user interface. And we're also developing Jupyter notebooks. These are used to illustrate how to access NED via APIs. They've been used in the workshops the AAS that have been given at the AAS meetings, including this one, to access NASA archives from Python. Improvements and additional examples are underway. And for more information about this, please visit the IPAC archive booth. Very briefly, heading toward the home stretch here. This is an overview of work, exciting work, high-level overview of things we have in the works and planned for the next few years. These center on three major themes: evolving the computing and database infrastructure, keeping the data current, and delivering new and improved science functionality. As far as meeting the demands of the computing infrastructure, we're extending relations in the database to expose more information about the probabilistic cross-matching and associations among objects, exploring high-performance scalable database to accelerate data ingest and query responses, continuing work on containerizing services for eventual cloud deployments, and we're building on initial success with applying machine learning to accelerate the finding and extracting and identifying the types of data relevant to NED. Excuse me one moment. Finally, this is a summary of the major data sets we're bringing into NED, very large catalogs, a source list from Hubble, JWST, Chandra, Euclid, further out SphereX. The next very large catalog we're integrating to NED is 3 billion photometric redshifts from pan-stars. In parallel, processing about 3,000 journal articles per year. We're also delivering new and improved science functionalities. I won't read through all of these. You can please stop by to talk to us at the exhibit booth for more information. Very briefly, what's depicted here is we're working on providing more information and making it easier to understand the relationship of objects in the hierarchy of the cosmic web, and also making it easier to run queries using pre-computed colors and derive physical quantities. Many science discoveries are being made directly from NED. This is a very brief summary of some of those. Again, please stop by and talk to us to find out more. I did give a review talk about this at a recent ADAS meeting. And lastly, as far as related happenings, we're working on updating a document regarding best practices for publishing your data in the journal articles. This is being done in collaboration with the other archives and also the journal publishers. We're seeking inputs on this from the community before we post it and integrate it eventually into instructions for authors. The goal is to streamline data ingest into the archives. If you're interested in using Python to access data archives, please visit the AstroPy and NumFocus sponsored project booths and attend the webinar. If you there's one being held by David Shoup on Wednesday at 4:30, and Python notebooks from the workshop that was given here was given on Friday are online in GitHub. In summary, NED is growing continuously in data and new functionality to facilitate science research. For information, you can reach us in any of these ways. Please consider becoming an ambassador to your projects. You can contact us through the help desk, Facebook, YouTube tutorials, and so on. And finally, thank you all. None of this would be possible without the NED team, the NED Users Committee, and of course, our funding agency, NASA. With that, I'm finished.
Thank you so much. That was a great presentation. Anyone can unmute themselves or go ahead and ask questions in the chat box, and I can read them out loud.
While waiting, again, I'd like to remind everyone to please drop by the IPAC NextEye Archives booth in the virtual exhibit hall for live demos, ask questions. We have people on staff throughout the whole meeting, and again, check out our growing collection of tutorials that are available on YouTube. There's links to those from the NED website, and of course you can again stop by and talk to us about it. Are there any questions?
We have one in the chat box from Pradeep. Are the Jupyter notebooks accessible on the NED website?
We have a link from the NED website, and the notebooks themselves are actually on GitHub. And again, stop by, or we can stop by. We'll give you that information if you drop into the booth.
Great. Everyone's saying great job.
Oh, great. Thank you. Thank you.
Mark Allen said, are you planning on running a Jupyter hub?
I think I would answer that with Mark. Hi, Mark. Drop by the booth. I think Shuchen could probably answer that better than I, but I would mention real briefly that over the next couple of years, there is work going on among the NASA archives to develop a science platform environment. And of course, we expect to plug NED into that when the timing's right, and almost surely that will involve a Jupyter Hub or equivalent type environment for accessing data in all the archives, including NED, in this integrated fashion. Yeah.
We have time for one more question. Is there a way to query all the star formation rate measurements for a given galaxy?
Good question. Yes, you can apply constraints in the by parameter search feature of NED, the lingo we use for this is parts of, basically these are components of galaxies or parts of galaxies. So you can constrain the patch of sky to contain the galaxy you're interested in, and apply the filter. So instead of getting whole galaxies out, you would just extract these components. You could also constrain specifically on H2 regions, for example.
All right, looks like we're out of time, but feel free to please stop by the booth to see if you have any more questions, or ask them in chat in the Slack channel, and everyone will be more than happy to answer you. So thank you so much, Joe. Great presentation.
Thanks very much. Thank you all for attending. We'll see you later.
Thank you. Bye-bye.